Hello and welcome to the second of a short series of videos about some of the level 3 questions on the frequency response topic. In this particular case we're doing this problem here, which asks you to construct a circuit given the position of the zeros and the poles. And we see in this particular circuit we're asked for two zeros at 0 Hz and poles with break frequencies at 6.32 and 25.8 kHz. So, first thing is to decide what topology of circuit we're going to be using. And here, the fact that we've got two zeros at 0 Hz is a dead giveaway. That means that there have to be two things which are forcing the output here to be 0 as the frequency gets lower and lower. And there's only two things here that have a frequency-dependent impedance, the capacitor and the inductor. Both of those have to be in the circuit such that they force the output here to be 0 at low frequencies. And that means that we need an inductor like that going to ground, so that at low frequencies, when the inductance has a 0 or very low impedance, the output here effectively gets connected directly to ground through the inductance. And also we have a capacitance here between the input and the output, so that at very low frequencies, when the impedance of the capacitance is enormous, no signal is getting from the input to the output either. Then we've got the resistor. There's two different places we can put the resistor. We could put it in parallel with the inductor, or we could put it in series with the capacitor. It actually doesn't matter. All that would change is the value of the resistor that we needed to find. The analysis is somewhat simpler if all the components are in series like this, so I'd suggest we just use that topology. It will work fine. Right then, all we have to do is to find the values. If we analyse this circuit, just work out its frequency response, analysing it in the usual way, using the potential divider equation, we would get that the frequency response is the impedance between the output and ground, in this particular case j omega L, divided by the impedance between the output and ground plus the impedance between the input and the output. Standard potential divider stuff. That would be this. That is not in the form of the ratio of two polynomials, so the first stage is to get it into the form of the ratio of two polynomials, and that means this term here in 1 over j omega c needs attention. Simplest thing to do, multiply up every term, top and bottom, by j omega c, and that would give us j omega squared lc over 1 plus j omega rc plus j omega squared lc. And I've just multiplied every term in this equation here by j omega c. That has two zeros at 0 Hz as required. Good. Now, we need to find the values of the resistance and the capacitance and the inductance to put the two poles in the correct place. Now, we've actually got 1 degree of freedom spare here. We've got three components that we can choose the values of, but we only have two constraints on the values of those components. And that means that we are free to choose the value of one component to be anything we like. We then have to work out the value of the other two components in relation to that known component. Capacitor is 100 nanofarads. Let's just use that one. It's as good a value as any, and work out what the value of the inductor and the resistor have to be. Okay, two really useful things to know about second order systems to solve this kind of problem. The product of the two poles is the square of the resonant frequency, and the sum of the two poles is minus the resonant frequency divided by Q. If we're dealing with real poles, as we are here, and just thinking about the break frequencies of the poles, we don't need to worry about the minus side. Strictly speaking, the poles have negative values, but their break frequencies or corner frequencies are positive. And the break frequency is the modulus of the pole, so we could just say that P0 and P1 are the modulus, the break frequencies of our poles, and get rid of that minus sign. Might make life a little bit simpler in doing the calculations. Okay, so comparing this equation here with the standard form of a second order system in terms of its resonant frequency and Q factor, that, as a reminder, is j omega over q omega naught plus j omega squared over omega naught squared. Comparing terms between these two equations shows us that omega naught squared is 1 over LC, and therefore L is 1 over omega naught squared times C. But we know that omega naught squared is the product of the two pole break frequencies, so that is 1 over P naught P1 times C. And we know all of these things. Only point to be careful of is that these P naughts here are angular frequencies in radians per second, and we are given the pole break frequencies in hertz. So we need to put in that factor of 2 pi to convert between hertz and radians per second. So we could work that out. It's 1 divided by the first pole, 6.323 kilohertz times 2 times pi to get it into angular frequency, times the second one, 25.83 kilohertz times 2 times pi, times the capacitance value, 100 nano, should give us the value of the inductor, 1.55 times 10 to the power of minus 3, which would be more normally written as 1.55 millihenries. Okay, type it in. That just leaves the value of the resistor to work out. The value of the resistor we get from looking at the Q factor, comparing the coefficients of j omega between these two forms of the equation here. We can see that RC equals 1 over Q omega naught. We also know that Q, from this equation here, is omega naught over P naught plus P1. So I could write R equals 1 over C times omega naught times Q, which is another omega naught, divided by P naught plus P1. Omega naught times omega naught is omega naught squared. P0 plus P1 over C omega naught squared. Omega naught squared is 1 over LC. So the C's cancel out. That's helpful. So we have, finally, R equals L times P naught plus P1. Really quite simple formula. That, if you put the numbers in, gives you the inductor, 1.55 milli that we've just found, times the sum of the two pole break frequencies. And remembering to convert them into radians per second again, 3 plus 2 times pi times 25.83 kilohertz gives me a value for my resistor of 313.1 ohms. 313 should be close enough. Okay, stick it in there. That's my circuit. Hooray. They're not actually that hard to do. The key things are to recognize what topology you need to get the number of zeros at 0 hertz. If we only had one 0 at 0 hertz, then I would have had to use a different topology, something like that, for example, or possibly something like this. Doesn't matter. You could work out values for these components for either of these topologies. If there was no zeros at 0 Hertz, then I'd be looking for something like this. That's probably the simplest way to attack that one. At 0 Hertz, there is nothing pulling the output here down to 0. And just remember those two useful formulas, that the product of the two poles is the square of the resonant frequency, and the sum of the two poles is the resonant frequency divided by the Q factor. Strictly speaking, minus the resonant frequency divided by the Q factor, because the poles are actually negative values. Yeah, that's about it. Good luck.